by now you're getting the sense that this is a lot more complex than just ordering a test and getting a positive result and saying the patient has the disease. And what we just did is showed you how the same test can perform differently depending on what your pretest probability is of a particular disease. So you have to actually rethink this each time you order a test based on how common or likely you think the disease is in the patient in front of you at that moment. So what we're going to vary this time is the sensitivity. We just showed you how a highly specific test can help rule in a disease. And what we want to show you now is how a highly sensitive test can help us move towards excluding the possibility of disease. So here's our 2x2 contingency table again. And we're going to take just a random disease. We're not going to give you the name of the disease and say it's there's a pretest probability of 80%, which is what we estimated Mrs. Trigliani's likelihood of pulmonary embolus was. This time, however, we're not going to use the same type of a test. We're going to use a new test that's got a great level of sensitivity and a sort of an average level of specificity. So we've changed the test characteristics and kept the pretest probability of 80%, similar to Mrs. Trigliani. So we're imagining a new test for her pulmonary embolus diagnosis. Again, we filled out the quadrants in this 2x2 contingency table, starting with our prevalence. We said that 80% of people who look like Mrs. Trigliani will end up having a pulmonary embolus in this environment. So we started with 1,000, 80% times 1,000 is 800. Then we looked at 800 as representing all people with disease and multiplied that by the sensitivity of 95% to fill in quadrant A and then by extension quadrant C. We then took all people who were healthy or free of disease, 200 in this population, and using our specificity numbers, multiplied 200 times 80% to fill in quadrant D, and by extension, quadrant B. And then we used our numeric values in A, B, C, and D to calculate our post-test probabilities of disease. A, 760, divided by A plus B, 780, is equal to 97%. That's the post-test probability of disease, or the proportion of people who test positive for the disease who actually have the disease. And our post-test probability of health is D, 180, divided by 180 over 1 plus 40, which is equal to 81%. That's our negative predictive value, and that's the proportion of people who test negative for the disease who are actually free of disease or healthy. Positive predictive value of 97%, negative predictive value of 81%. But what we've learned in the last couple of slides is we're also interested in the false negative rate, which is equal to 1 minus the negative predictive value. That would be 40 divided by 40 plus 180, or in this situation, 19%. And that's the percent of people who test negative for the disease who actually still have the disease. And that's going to help us complete our likelihood column or ruler over here. So our pretest probability in this environment is 80%. If we got a positive test with this particular test, it would move us from 80% likelihood up to about 97% likelihood. So if you weren't happy with just being 80% likely, this test would definitely make you feel a lot more comfortable getting you up to the very likely range. What is a negative test going to mean for us? Well, we started with a pretest likelihood of 80%, and a negative test will give us a post-test possibility of disease of about 19%. 19 to 20% if you want to round it up to average things. So again, if you look at the impact of movement on the test results, a negative test, because it's a very sensitive test, moved us way down. There was a much bigger delta between the pretest and the negative test than there was between the pretest and a positive test. So it moved us from likely to between unlikely and very unlikely. So that was a really helpful test, I think, for us. Summarizing that in words, when a disease is likely, a positive result from a very sensitive test can slightly increase your certainty that the disease is present. We went from 80% to 97% in this particular case. But even more interestingly, when a disease is likely, a negative test result from a very sensitive test makes you much, much less certain that that disease was present. We went from 80% all the way down to 20%. Now, is that low enough for you to exclude the disease? To a large extent, it depends what you're going to do next. If it's a really, really serious disease and missing it would be catastrophic, you probably are going to need another test to see if you can get that post-test probability even lower. But in some situations where the disease is not particularly serious and you can say it's likely that you don't have it and not be too worried about what's going to happen, that might have been a big enough move. So, we looked at the impact of varying sensitivity and specificity with a very common disease. And then we looked at sensitivity and specificity in uncommon diseases. Let's look at this middle range, because people who know a lot about testing will tell you that tests have their biggest impact when the pretest probability is in the moderate or uncertain range. And that's where you should put most of your testing dollars if you were going to be a betting person. So we're going to try a particular condition where we think the likelihood going into the testing environment is only about 50%. So that meets our definition for uncertainty. So again, we filled out our 2x2 contingency table, and we're going to use sensitivity and specificity of 80 and 95% like we did for the last case. Here's our total population. 50% times 1,000 is 500. We multiplied that 500, which represents all people with disease, by our sensitivity to fill in quadrant A, and then by extension, quadrant C. And then we multiply quadrant F, which represents all people who are free of disease, by the specificity to fill in quadrant D, and by extension, quadrant B. And then we use our post-test probability formulas, positive predictive value, to calculate the positive predictive value. So that's all who test positive for the disease compared with the people who actually have the disease. So 475 over 575, and that's 82%. And then our post-test probability of health, or negative predictive value, is 400 divided by 425, D plus C, and that's equal to 94%. And remember, we like that statistic of 1 minus the negative predictive value, because that tells us how likely disease is even if the test is negative, and that would be 25 over 425, and that represents 6%. Okay? So, we moved then from a pretest probability of 50% if our test is positive, we'll move all the way up to 82%. That's a pretty good move. And if our test is negative, we move from a pretest probability of 50% all the way down to 6%, which is pretty good at ruling out a disease. So you see a very sensitive test, uncertain pretest probability that is about 50%. If the test is negative, it's going to help us rule out disease. Remember what we had said, a sensitive test, when negative, rules out disease. This is where that statement comes from, this particular scenario. What we've just spent time doing is demonstrating Bayes' theorem. And Bayes' theorem is important for you to know about by name, because often people will ask you about it on rounds, and it will be terrific if you can say, yes, of course I know what Bayes' theorem is, and this is how we use it in the clinical problem-solving arena. In short, Bayes' theorem can be summarized as this. First, tests always help us move the probability of disease up or down from where we started in our pretest probability estimation using our illness script matching and our tiering of our differential diagnoses. If the pretest probability of disease is very high, like we saw in Ms. Triglione, a negative test applied in that situation is more likely to be a false negative test than a true negative test. What they're saying, of course, is be careful. A negative test really can't rule out most diseases if you start with a very high pretest probability. with the exception perhaps of a very, very sensitive test, and we'll talk about that in a minute. The corollary of that, of course, is if the pretest probability of disease is very low, a positive test is more likely to represent a false positive result than a true positive result. Essentially what it's saying is if you really don't think the person has the disease, a positive test shouldn't make you conclude the patient has the disease. It should make you think about whether or not that's a false positive. And of course, by extension, tests have the highest impact if your pretest probability of disease is in the uncertain range, around 50%, or anywhere between really 30 and 70%. So that's Bayes' theorem in a nutshell. It says be careful with interpreting diagnostic tests. So probably all of you are scratching your head at this point in time and sort of saying, she promised us a heuristic, let's get to it, because most of us don't really want to do this math all the time. And I can tell you that over time, though, you begin to sort of gestalt this, and here's some ways in which you can move forward in that kind of gestalt manner. But you still are going to need to assess the pretest probability of disease, and that's why starting off with that clinical matching of illness script to disease illness script and tiering of your differential diagnosis is absolutely essential every time you see a patient. So the heuristic or rule of thumb was something that Mitch Meadow and I came up with in working on this course, and it's published in that evidence-based medicine article that I referenced earlier on. And in general, what we say is that good tests with good sensitivity and specificity, generally in the greater than 85% for both of them, are able to move the likelihood of diseases up or down one category on our likelihood bar. And remember, they had 5 categories ranging from very unlikely to unlikely to uncertain to likely to very likely. Those were our categories. So you can move the likelihood of a disease up or down one category with a test, but not too much further, except for 2 special cases. If you really need to rule out a disease regardless of what the pretest probability is, you need to find a test that has a sensitivity of greater than 99%. Anything short of that will not allow you to definitively rule out that disease with a single test. And if you need to really rule in a disease, you need to find a test with a specificity of greater than 99%. The test has a lower specificity than that. You're not really going to be able to rule it in with simply one test. Tests are generally not needed for conditions that you rate clinically as very likely or very unlikely, except if the consequences of a misdiagnosis are extreme. So if you feel like you need to test for something that you've already estimated to be very unlikely or very likely, you may need more than one test, because one test will get you just one category up from very unlikely to just unlikely, or one category down from very likely to just likely. And we're going to illustrate this on the next couple of slides. Let's try a clinical example using this heuristic. And the question I'm going to pose for you is this person's chest pain due to coronary artery disease, CAD? Well, from lots of population studies, we have published data that shows that middle-aged men who have classic anginal chest pain, described as substernal chest pressure that comes on with exertion and is relieved by rest, have a pretest probability of coronary artery disease of about 70%. If we apply our heuristic and we know that the next level test of exercise treadmill test does not have a sensitivity or specificity of 99%, but they're both pretty good tests, a positive test would move him from a pretest probability of likely to a post-test probability of very likely. So that's what our heuristic would show, and if we took the time to do that 2x2 contingency table, I could prove this to you mathematically, but I suspect you'd rather that I didn't. So what, however, about a negative test result? And remember, we've looked at this a lot on our likelihood bar here, or our likelihood ruler, and we know that a negative test can still be present in someone with the disease. That's the false negative rate. And our heuristic says that this test would move us from a pretest probability of likely just to a post-test probability of uncertain. So be really careful. That doesn't rule out the test rule out the possible diagnosis. And this is critically important in something like coronary artery disease, because we don't want to reassure this middle-aged man that his anginal chest pain is not due to coronary disease just because he had a negative test, because we know that test was not powerful enough to move it all the way to very unlikely. It just moved it to uncertain. Let's take the same situation and apply it to a different population. And here's an example where the epidemiology really changes the pretest probability. In this case, we're dealing with a middle-aged woman, and we know that women have, at a given age, proportionally less likelihood of coronary artery disease, particularly premenopausally. So, middle-aged woman, same anginal chest pain. From population studies, we know they have a pretest probability of coronary artery disease that's 30%. It puts them in the unlikely category. Now, remember what our Bayesian theory said. If you start with an unlikely category, a positive result is more likely to be a false positive than a true positive. And using our heuristic, we know that if her test result is positive, at best we can move her into the uncertain range. But if her test result is negative, we can feel pretty comfortable that she doesn't have the disease. So that's the rule of thumb. A good test, but not a fantastic test. That is, a test with a sensitivity and specificity that's less than 99% can move our pretest probability up or down one category based on whether the result is positive or negative, respectively. So that's one way you can use this information in the clinical setting. Another way is to use what's been known as a Bayesian Nomogram or a Fagin Nomogram. And you can find these all over the web. In fact, actually, there are online calculators, and one is referenced here, where you can plug the data in, and it will give you the post-test probability if you insert your pre-test probability and the sensitivity and specificity of the test that you're using. There's also lots of pocket tools that you can buy online if you want to carry one of these around to help you in your day-to-day decision-making around clinical problem solving. So let me just introduce one last set of formulas for you, just to show you how this nomogram works in case you don't want to use the online calculators. This requires that we take sensitivity and specificity and convert them into a global statistic known as likelihood ratios. And likelihood ratios are the likelihood that a given test comes from someone who has the disease rather than someone without the disease. So the likelihood ratio of a positive test is the likelihood that the positive test comes from someone with the disease rather than someone who is free of the disease or healthy. And the formula is sensitivity over 1 minus specificity. So you might understand that from your formulas as being the true positive over 1 minus specificity, which is the false positive. The likelihood ratio of a negative test is the likelihood that a negative test came from someone with the disease versus someone without the disease, and that's a false negative, 1 minus sensitivity over the true negative. Now, these formula aren't all that important for you to memorize, just so that you know how to do it in case you had to do it. I just encourage you to look them up. But let's show how we use our nomogram. Let's use our Fagin Nomogram to help us interpret our VQ scan results. We know from our previous slides that VQ scanning in patients with suspected pulmonary emboli has a sensitivity of about 77%. It's not very good. And a specificity of 97%. It's actually quite good. So the likelihood ratio combines those two test characteristics into one number. And if we plug in the formula, the likelihood ratio of a positive test is 25. That means if we get a positive test, it's 25 times as likely to have come from someone with the disease as it would be to come from someone without the disease. If we get a negative test, though, we use the negative likelihood ratio. And we can see that a negative test is 0.24 times as likely to come from someone with the disease as it is to come from someone without the disease. So let's apply that using our Fagin Nomogram. And what we will do is you first put your ruler or straight edge at the pretest probability of 80%, and then you connect it up through the likelihood ratio for a positive test, if that's what we're looking at. And you see that starting with a pretest probability of 80, connecting through the likelihood ratio of 25, which we calculated to be the case for this particular test, gives us a post-test probability of 99%, and we've ruled in the disease. So that's actually really good news. Specific test, when positive, rules in the disease, remember? Let's look at the negative result with a high pretest probability. So again, we put the straight edge at 80, but this time we connect to a likelihood ratio negative value of 0.24, and we end up with a post-test probability of 40%. Now, as you see, we move from 80 to 40. That's really not enough to rule out the disease. Why didn't it move it farther down the nomogram? Because remember, our test isn't very sensitive. And our SNOUT acronym, that sensitive test when negative rule out a disease, only works if the test is sensitive, and ours isn't particularly sensitive. Well, let's look what would happen if we changed our pretest probability from 80% down to 10%. Remember Mrs. Garcia, we thought she was about 10% pretest probability. We start with our straight edge at 10%. If the test is positive, we connect to the 25 positive likelihood ratio, and we move up to 80. So even in a low probability setting, a specific test moved us up quite a bit. Perhaps not as far as we needed to go, but it was really a big jump. But a negative test starting at 10%, connecting to 0.24, brings us down to about 2%, was good enough to rule out the disease in this setting. So this has been a pretty intense module. I hope you're going to take home these key issues. Number one, chosen carefully and used correctly, diagnostic tests can help you decrease your uncertainty about the diagnoses you're considering. But beware of a common mistake. A common mistake is to consider diagnostic test results as 100% accurate, rather than simply an aid to decrease your uncertainty. Using the test correctly is going to require that you calculate your pretest probability of the disease you're considering. Don't forget to use your tiers and translate them into numbers if you want to use the mathematical way of calculating post-test probability. Or use your heuristics to guesstimate what the impact of a positive or negative test might be. I, for one, really like using the nomogram and hope you'll find the opportunity in the next week or so as you're working with clinical problem-solving tests at home and on the homework to try the Fagin Nomogram calculators referenced in this work. So our final quiz for 4.8. Diagnostic tests are most helpful to, number one, rule in a disease that is a tier 1, likely or very likely. Number two, rule out a disease that's tier 1, likely or very likely. Number three, rule in a disease that's tier 3, that is a low pretest probability of disease, or to rule out a disease that's tier 2. And the answer, of course, is number 4. Diagnostic tests are most helpful in cases of diagnostic uncertainty, which is our tier 2 type diagnoses. Thanks for listening, and we'll see you again next week.